So last time we actually did several examples applying the rules of derivative, quotient rule, product rule. Now let's keep doing more, okay? So this time we're gonna talk about the chain rule. What's the chain rule for? This is to find derivative of composition of functions, okay? Now, for the previous rule, it was a little bit easier to identify when they needed to be used because, you know, a product, you can see there is a product taking place. A quotient, you can see there is a quotient taking place. Now, you need to be able to identify when a composition is taking place, okay? So I guess that's when this becomes a little bit, I guess, a little slightly more difficult because you have to make sure that you understand what a composition is and you can decompose functions. Okay, like if you say composition, what's the outside function? What's the inside function? What are the two functions that are being composed? Okay, so we're gonna practice, do a little bit of problems like that before we get to the rule. But anyways, let me tell you what the rule is. That way, you know why we want to decompose functions. All right. So let's see. Right, so the chain rule. Again, to argue the chain rule is a little bit more complicated, so it's going to take us some time. You can take a look at the book. The book has an informal discussion on how the rule arrives, okay, how you can obtain the rule. But I would rather just go straight to the examples. So let me put here theorem, or let me first say goal. The goal of this is to find derivative of composite functions. Okay, and for example, we want to find derivative of, let me write all the things that I have here. Something like this, 1 over 1 plus x. What is this? Something like the derivative of the square root of 3x squared minus x plus 1. What is this? Derivative of sine of 2x. Let's say. What is this? Okay, that kind of this kind of functions now we want to be able to compute. And of course, there's a rule for this that's called the chain rule. But remember, the first thing that you have to do is you have to be able to look at a function like this and understand that a composition is taking place. Okay, you have to be able to look at this and understand that a composition is taking place. So let me ask you, do you know what I mean by the word composition? No? So some of you don't. So remember, when you have two functions, there are several operations that you can do. You can add them, subtract them, multiply, etc. Another thing that you can do is plug one function into the other. Okay? When you do this, we call this function composition. So recall, if f and g are two functions, then their composition is the following. So there are two compositions that you can do. You can do f composed with g, or you could do g composed with f. So this is the special notation that we use for composition, this little circle. But what this means is this is defined to be f of g of x. And this one here is g of f of x. So basically what it says is this is a new function, and how do you evaluate this function? Okay, give me an input, then this input is plugged into g first, g is going to do something to it, give you an output, and then that gets fed into f, and then give you the final output. Okay, so you can think of, remember, functions are like little machines. You give it an input, they give you an output. So the picture for this would be like this. Let's say this is the machine g, and then we have two machines in series. Okay, so typically this is what you would do. You feed the function an input, and then it's going to give you an output. And that's what the function does. But now here you have another function that's this output is going to go into this one. Okay? And then the output is f of g of x. That's why we call it function composition, because it's like you put these two machines one after the other. Do you understand this? And then the other way around, that's the other picture. So here f is done first. and then g. So x goes in, f of x comes out, it goes into g, and then g of f of x comes out. Okay? That's function composition. And then, of course, the challenge is that if I give you a formula, you have to be able to tell me what's f and what's g. Okay? So in this case, we refer to this guy, the outside function, because that's the one that you do last. If you look at this, outside, because this is the outside. You see that? So this is the outside, and I'm going to be calling this one the inside function. The one that you do first is the inside, the one that you do last is the outside. And of course, you can have a composition of 2, 3, 4, 5, 20 functions. Okay? All right, so let me give you the rule, and then before we use the rule, we're going to train ourselves or practice how to decompose functions. So to decompose function means I give you this one, I want you to tell me the f and the g. It's called decomposing function. Okay? So I guess let me do a little example here. If f of x equals x plus 7 and g of x equals x cubed, let's see, can you tell me what's f composed with g? What is this equal to?
X squared from x cubed plus 7.
So let's see, this is f of g of x, right? So that just means put g into f, so that would be x cubed plus 7. Does everyone understand this? Now, what is g of f? So g composed with f?
X plus 7 cubed.
X plus 7 cubed, very good. So this means plugging f into g. So wherever you see an x here, just put the entire formula and you put it there. So that's x plus 7 cubed. And hopefully you agree that these two things are not equal. In other words, the order in which you do composition matters. It matters who is outside and who is inside. Okay? So if I give you this function now, this is what it means to compose a function. Okay? So this is function composition. Now, sample number 2, decompose the function. So it's doing this problem backwards. So if I give you the function y equals x plus 7 cubed, I want you to tell me an f, and I want you to tell me a g. Now, typically, by f, I will mean the outside function. In other words, you want to think of this as being f of g of x. But this is all you have. Your job is to tell me what is f and what is g. So doing it backwards. Okay, that's what we're going to be doing now. In College Algebra, you did this. You give functions, and they ask you for the composition, and then you found domain, and a bunch of other stuff. Now here, we want to decompose because we need these little pieces for what we're about to do. So can you tell me, it kind of comes from the top, but anyways, can you tell me what's f and what's g in this case?
F is x cubed.
F is x cubed, and what is g?
X plus 7.
X plus 7. Does everybody understand this? And hopefully these are the two things that come to your mind. Maybe you get them in the wrong way. Then always check. Plug one into the other and make sure that you get the function that I gave you. If you get something else, then that means you need to switch. Okay? So if you don't get it right, let's say that you would have told me that f is x plus 7 and g is x cubed. So, you confuse the inside and the outside. When you check, by plugging in, you will get this expression rather instead of this. So you know that you did it wrong, so you just switch. Okay? It's very easy to check whether you did it correctly or not. So we're gonna need this, okay? But before we do that, let me tell you what the chain rule says. So theorem, and we're gonna practice more decomposing function. So this is called the chain rule. And as we do examples later, you're gonna see why we call it chain. And here is what it says. So suppose that we have a composition of two functions. So what I'm about to write is the formality of this. So if y equals f of u is a differentiable function, of the variable u, and if u itself turns out to also be a function, and u equals g of x, is a differential function of x, okay, then the function f of u, okay, then y, which is f of u, can also be considered as a function of x, right? So here we have a function of the variable u, but then what I'm saying is that this variable u is also a function of another variable that we're calling x. So the original function, you can think of it as a function of x by looking at the composition, okay? So when this happens, then because these two guys are differentiable, what the theorem says is that the composition is also differentiable, and we have a formula to find the derivative, okay? Then y equal f of g of x is differentiable with respect of x, and moreover, we have a way of finding the derivative. So I can ask for derivative of y with respect of x, and the way that we compute this is as follows. This is the chain rule. dy dx is first do the derivative with respect of u, because y is differentiable function of u, so you can talk about dy du, but then you multiply this by the derivative of u with respect of x. Okay, so it's dy du times du dx. This is kind of, if you think of this as being operators, okay, which they are, these are called differentials, but you learn this in country. If you think of this as operators, notice that you can cancel this guy and then you get the dy dx. Okay, it's kind of easy to remember this form. This is called the Leibniz notation for the chain rule. Now, typically we don't think about it this way, so I'm gonna write the other way. So it's called the Leibniz notation. So equivalently, so dy dx stands for the derivative with respect of x of f composed with g. Okay. All right. So because y equals f of g of x. Now what this is telling me is take derivative of y with respect of u. So that's just derivative of f with respect to this variable. So the way we write that is like this: f prime, then plug in g of x, and then times, now du dx, remember u is equal to g, so that's just g prime. And this is typically, the way this is written. So this is what we call the chain rule. And in words, it says when you take the derivative of the composition, what is this equal to? You take the derivative of the outside function, and plug in the inside function, times the derivative of the inside. Okay? In words, that's how you say it. So that's why you need to know what's your f and what's your g. Otherwise, you cannot use the rule. Okay? So the derivative of a composition is the derivative of the outside function evaluated of the inside function times the derivative of the inside function. Okay? So that's in words what's written, and you're going to be using this a lot because typically when you see a function, typically it's going to come in the form of a composition. Okay? So keep this in mind. Are there any questions about the rule? We're going to use it now, but do you understand what that box is saying? Do you understand what's written in the box? Yes? Okay, so hopefully you agree that to be able to use this, the first thing is that you need to know, given a function, what's f and what's g, right? So let's practice that. I'm going to give you some functions, like the ones that I gave you up here at the beginning, Our job is to identify f and g. Okay? That's what we want to do. We're going to take derivative later. Right now, let's decompose those functions. So, sample number one. So, a composite function y equals f of g of x is given. Identify f of x and g of x. Okay? So I want you to tell me the outside function, that's f, and the inside function, that's g. All right, so 1 over x plus 1. Let's do sine of 2x. Let's do square root of 3x squared minus x plus 1. Tangent square of x. Okay, so here we have, how many? 6. Here we have 6 functions. Let's decompose. Okay, so let's find f of x. And let's find g of x. Okay, so let's see. I'm gonna do the first one, and then hopefully it's gonna get you started for the rest. So let's see. You have to think about 2 formulas. So when you plug for f and g, so when you put g inside f, I get the formula 1 over x plus 1, right? So what do you think we should do? Well, the outcome, the result is 1 over something. Do you see this? 1 over something. So hopefully it's natural to think about the function 1 over x. That's a function that tells me 1 over something. Okay? And then the moment that I declare f to be 1 over x, 1 must g be x plus 1. So now if you plug in g into f, we're going to get 1 over x plus 1. Which means replacing the x in f by the function g. So you get your 1 over x plus 1. Do you understand this? Yes? So that's what it means to decompose the function. All right, let's see. Who can tell me for b? What's f?
Sine of x.
And what is g? Very good. Yeah. So, does everybody agree with this? That the outside function here, and most of the time it's very obvious what the outside function should be. Okay? Sine function. Think about it, the function that you do last. So one way to think about it is when you want to evaluate this expression, what do you do first? Do you do the sine or the 2 times x? If I plug in something for x, what do you do first? The times 2 or the sine? You first do times 2, and then you do sine, right? Same thing here in part A. What do you do first when I plug in something for x? The 1 over or the plus 1? You do the plus 1 first, so that's your inside function. Okay? Whichever you do first, that's the inside. And then, okay. All right, so let's see. Tell me this, and then I'm going to give you some time to do the others, and then you tell me the answer. How about this one? Okay, good. Square root. The inside?
3x squared.
3x squared minus x plus 1. That's one entire function. Does everybody understand this? Okay, so try the last 3. I'll give you 2 minutes. Do you have a question or you want to say this?
No, I haven't.
Let's let everybody try it first. And then of course, when we say this, you know, we are always looking for a non-trivial decomposition because there is always a trivial decomposition. What's a trivial decomposition? Just give me whatever formula you want. It can be, you know, the craziest formula that you can think about. I don't know, whatever. And then I can just say, okay, the trivial decomposition is f of x is equal to x, and then g is my whatever. What happens if I do the composition? What do you get? I plug this into here, so you get, you know. Yes, you get what you started with, but this is not helpful. This is trivial. You can do this with any function. Okay? So what I want you to do is I want you to give me two functions, none of them being the identity function, the function x. Okay? So because technically this is the composition, but this doesn't help us. Okay? All right, so let's see. D. What is it?
Tan f of x equals x squared.
F of x equals x squared. And what's G?
G of x equals tan of x.
Tangent of x. Good. Does everybody understand this? Okay. Don't take it personal.
No, I'm just saying I got it.
Okay, good.
Yeah.
How about E?
X
X cubed. Good.
and then x squared plus 1.
Okay, good. And how about F?
-7
Over x squared.
Very good. -7 over x squared.
2x minus 3.
2x minus 3. Good.
I can't tell this is 3 from here.
Okay.
Yeah. Sorry, it's just smart board's not mine.
So he's sitting in the front. Okay. Are you guys okay with this? Yes? So let me see. Could you give me three functions whose composition give me f? So I claim that we can write f as, so you know, the last one as f of g of h. Okay? So, and you know, sometimes, for example, if I would have given you this function, there are three functions at play here. Do you see them? What's the outermost function?
X squared.
The x squared function. Remember, what's the last thing that you would do here? The square, right? So that's the outermost function. I'm gonna be writing diagrams like this. You will see why later. Then what's the second outermost function? The sine function. And then what's the innermost? 3x. So do you see this as a composition of three functions? So can you see that in the last one? Could you write it? So what would that be? Very good. -7 over x, then x squared, then
2x minus 3.
2x minus 3. Good. So there will be instances in which we have composition of 2, 3, 4, you know, then here I could do, I don't know, what if I have done this? How many functions are we composing now? 4 functions. You have to be able to identify all of these in the correct order, right? So here I guess I should stick a square root here and then 3x. Okay? We will see that when we do examples. Remember, all right, so questions about the composing functions? No? Okay, so now our job at hand is to take derivatives. So let's go ahead and let's use the chain rule by taking the derivative of all of these functions. Okay? Again, typically nobody's going to tell you to use the chain rule. I will just ask you to find the derivative. It's your job to realize that a composition is taking place, and therefore chain rule needs to be used. Okay? All right, so let me remind you what the chain rule says. When you need to take the derivative of a composition, you need to identify what's the outside, what's the inside function, and then the rule is derivative of the outside, plug in the inside, times derivative of the inside. Okay? Let's see, I'm gonna do a couple here, and then, so I'm gonna do the first three, and then I'm gonna let you do the last three. Okay, and then we do it together as usual. And let's do the first three so we get used to it. Okay, so the second example is find the derivative of the above functions. Okay, so the first one was y equals 1 over x plus 1. If you want, you can write your f and your g, but typically once you get used to this is just in your head, just happening in your head, okay? But for the time being, I'm gonna write it down so you understand what I'm gonna do. So remember, f here was 1 over x, and g was
X plus 1.
x plus 1, okay? And we're thinking of this as being f composed with g. So when we find the derivative, when we find y prime, according to a chain rule, this is derivative of f evaluated at g times g prime. Right? That's what the chain rule says. All right? Let's see what that is. So I need f prime. So let's compute it. What is f prime? What's f prime? Okay, so 1 over x is going to pop up below, so you should remember it. And square root of x is also going to pop up below, so you should remember the derivative. If not, how do you do it? You need to write this as x to a negative 1 and then use power root. Yes? If you do that, then you get negative 1 over x squared. You know, just write it as x to a negative 1. And when you use power rule, the negative 1 comes down, and then you have negative 2. So that's negative 1 over x squared. Are we good with this? That's f prime, and since we're gonna need it, let's also write down g prime. What's g prime? 1. Good. So now let's use the rule. So what's the rule says? Derivative of f, and then plug in g. So that would be negative 1 over. Now I have to plug in g. Yes, and then times g prime. What's g prime? 1. So this is just negative 1 over x plus 1 squared. So derivative of 1 over x plus 1 means negative 1 over x plus 1 squared. Questions? Did you understand this? Okay, so we do the next one. So we have y equals sine of 2x. Now, I'm not going to write f and g anymore. Let me get you more used to the kind of things that I like to write. So remember, we already identified f and g, so I'm going to use this chain notation. Okay? Chain because it's one after the other. That's why I'm calling it chain notation. So here, the outside function is the sine function. Then the inside function is 2x. Do you understand this? And I guess if you want, you can probably, it's just that it's weird, but you can probably put the arrow this way, because 2x is the one that's go into the sign. But it's strange, so I put it like this. Okay. The point is that I'm writing from the outermost function all the way towards the innermost function. Now down here, I'm going to write a new one in which I'm going to write the derivative of each guy. So what's the derivative of sine?
Cosine.
So cosine, let me put it here. And what's the derivative of 2x? 2. Okay? So we're going to do something with those things and write it here. So now, if we want to find the derivative of this, what does the chain rule says? Derivative of the outside, which is this guy, then you plug in the inside function, this one over here. Okay? So that would be cosine, that's the derivative of the outside, evaluated at the inside function, which is 2x, times the derivative of the inside, right? Just 2. So the answer is 2 times cosine of 2x. So when it's just two functions, you don't really need to do this little picture. But the moment that you have 2, 3, 4 functions, This is very helpful because it allows you to keep track of what you're doing. Okay? So once we get to expressions like this, then I'm going to show you how to successfully use this picture. Okay? But when it's just composition of 2, you can just do it. Derivative of the outside is cosine, plug in this guy, times derivative of the inside. That's typically the way we think about it. All right. Questions? No? Okay. We'll do one more and then I'll let you try the others. So we have y equals square root of 3x squared minus x plus 1. So for the time being, let me just put it here as a sequence, right, of composition. We need the derivatives. So what are the derivatives? Derivative of square root of x. 1 over 2 square root of x, right? And what's the derivative of the other one?
6x minus 1.
6x minus 1. Everybody understand this? Yes? 6x minus 1. Okay, so now let's activate chain rule. So what's y prime? Derivative of the outside. So that's 1 over 2 square root of. Now plug in the inside, which is 3x squared minus x plus 1. Let me put the formula. So that's f prime of g of x times g prime. Okay. So this part here is 1 over 2 square root of
3x squared
minus x plus 1, and then times, then
6x minus
derivative of g, which is 6x minus 1. In other words, the answer is 6x minus 1 over 2. Okay. Questions? Any questions on this? No? Okay, so go ahead and find the derivative of the last three. I'm gonna give you like 4 minutes, right? And then we do it together. Tell me what you got and so on. So do D, E, and F. And you already have the decomposition there. I'm gonna write the chain rule on the board in case that you don't remember. So derivative of F composed with G equals F prime evaluated at G times G prime. Okay. Okay, so for D, what's the outside function? Square. And what's the inside function? Tan. Okay. So what's the derivative?
2 times tan x times secant squared of x.
Very good. Does everybody understand this? So again, this part right here corresponds to derivative of the outside evaluated at G, and then this part right here is the G prime part, because the derivative of tangent is secant squared, right? Questions? And here there is not much simplification taking place. I mean, tangent is sine over cosine, and this is 1 over cosine squared. So you could write 2 sine over cosine cubed. That doesn't really help much, so we just leave it like that. Okay, how about the next one? What's the composition? What's the outside? X cubed, the inside? Square plus 1. Okay, so what's y prime?
3x squared.
What is it?
3x squared.
Like this?
Well, I got 3 times x squared plus 1 all squared.
Good.
Times 2x.
Very good. So the derivative of the outside, that's 3x squared, but then you have to plug in the inside function, right? Instead of x, you have to have x squared plus 1. That's this piece right here. Do you see that? Yes or no?
No, I thought you were asking for the derivative of x cubed.
Oh, no. So the derivative of the outside evaluated at the inside, that's this part, and then times the derivative of the inside, which is 2x. Okay? So what's the final answer? 6x times x squared plus 1 squared. Questions? Do you understand how to use the rule? Okay. Okay, the next one, what's the outside function?
Negative 7 over x squared.
Negative 7 over x squared. What's the inside function?
2x minus 3.
2x minus 3. So let's see, let's put the derivatives down here to help us. So what's the derivative of the outside?
14x cubed.
So good. 14x cubed. Does everybody see how to get this? So you need to rewrite it as x to the negative 2. Then when you take derivative, negative 2 times negative 7 would be the positive 14, and then you have x to the negative 3. Do I need to write this down, or you guys understand?
Please write it down.
Write it down. Okay. So then derivative of negative 7 over x squared, you just write that as negative 7 times x to the negative 2, and then you use, negative 7 is a constant, so you keep it there, and then power rule. Negative 2 comes down, and then x to the negative 3. So that's where you get the positive 14, and then the x cubed in the bottom. Yes? And the derivative of this, what is it? Of 2x minus 3 is 2. Okay, so with this at hand, we are ready to find y prime. So derivative of the outside, 14 over x cubed, but then we have to plug in the inside. What's the inside function?
2x minus 3.
So that would be 14 over 2x minus 3 cubed. Yes? And times the derivative of the inside. What's the inside? Times 2. So we get 28 over 2x minus 3 cubed. So once again, this piece right here is the f prime of g of x, and this one here is the g prime, where this is our f and this is our g. Okay, questions? No? Okay, so let me make an observation here. Let's take a look at E. So notice that when we did this derivative, it actually, if you look at this step, it kind of looks like the power rule, right? It's just that instead of x to the n, you have a function cubed in this case. But basically, if you look at it, what do? You plug the 3 down, subtract the 1, right? So far so good. This stays the same. And then the only new feature is that we multiply by the derivative of what was inside. That's because of the chain rule, because there is a composition. Okay? We call this effect the general power rule. Okay? So what the general power rule says is anytime that you have a function raised to a power, how do you take the derivative? Just do the power rule thing, bring the exponent down, subtract 1, but then remember that you have to multiply by the derivative of the inside, because that's chain rule. There is a composition. Okay, so I'm gonna write that down. So you don't have to be thinking about f and g and so on. If you have a function to a power, it's very easy to do it that way. Okay, so general power rule. And basically it says the following. So if y happens to be the following, let's say is some function, let's call it u of x to the n power, where u is differentiable and n is any real number, then the derivative with respect of x of this is n times u to the n minus 1, and then of course times u prime. Okay, so just use the usual power rule, bring the n down, subtract 1, but then times the derivative of the inside because of chain. Okay, so yes, shorthand notation without too many x's. If you have derivative with respect of x of u to the n, this is n u n minus 1 times u prime. Okay, remember this is a function of x. So as a quick example, let's say that we have the function f of x equals 3x minus 2x squared to the 5th power. If you want to find f prime, this is our u right here, so this is something to the 5, so just use the general power rule. So this is 5 times this function to the 4, but then times the derivative of the inside. What's the derivative of the inside?
3 minus 4.
Good. Do you understand this? Okay. So now let's do more examples. I'm going to give you a bunch of functions. Just practice taking derivative, okay? So let me write it down. So find the derivative. Let's see, the 1, let's do y equals let me leave this number 2. So let's put something simpler first. Let's do cosine of x minus 1. And let's do f of x equals, and of course here now we start combining rules, right? For example, on number 2, what do you need to do? First, notice that this is a product, so the dominating rule here is a product rule, right? But as you do product rule, at some point you have to focus on the derivative of this guy, right? Now, how do you do the derivative of this? Chain rule, because there is a composition here. So it's a product rule, and inside the product rule you have a little chain rule. Do you understand this? So do that one. Then let's do okay. This one. Do 6 and then we do more. Actually, let me put 7 here. I'm gonna give you about 10 minutes to try this. If you get stuck, you can raise your hand, you can ask me, talk to your classmate, whatever. Just try as much as you can, try to do this, and then we're gonna discuss it together. And I want you to try first. So in case you don't remember, so here's the chain rule. Let me put here the product rule. So remember, this is f prime times g plus f times g prime. And then I'm gonna put here the quotient rule as well. Derivative of the top times the bottom minus the top times the derivative of the bottom divided by bottom square. Okay. Joshua Acevedo, Eri Acosta, Rebeca Álvarez, Brian Arango, Marcos Bucarito, Oscar Camejo, Shawn Campbell, Cassandra Castellón, Carlos Concepción, Diego Concha, Darío de la Nuez, Ulises del Pino, Lester Fernández, Violeta González, Jorge Guntín, Anthony Guzmán, Cecilia Izquierdo, Yanin Yaurado, Isabela López, Robert López, Cristín Matos, Giovanni Maya, Millard McLeod, Ashley Medina, Javier Méndez, Carlos Molina, Alejandro Morales, Macy Reyes, Kayla Ribeiro, Rebeca Romero, Roberto Sáenz. Cáceres Tapia. Víctor Torres.
Here.
Joao Valadares. Briano Valencia. Manuel Valencia. Fabricio Viña. Mohamed Sia. It's better to do number 7 before this one. That way you get used to more than 2 compositions. You see that how many compositions are here? 4. 1, 2, 3, 4. 4 compositions, 5 functions, right? Here, how many do we have?
3.
So I guess 2 compositions, 3 functions, right? 1, 2, 3. So it's easy to do this one first, and then when you get used to that, then try this one.
Is that a 12 up there?
12. Let's do these problems. You have some time to try your computation. Now let's do it together. Otherwise, we're not going to have time to finish everything together. Okay? Okay, so give me a sec. All right, so solution. Let's do this one by one. So let's see. The first one was cosine of x minus 1. Okay, so what's the solution?
Negative sin.
Sine, okay?
Sine. Parentheses x minus 1.
Very good. Does everybody agree with this? Again, just to see quickly, the composition here is cosine is the outside function and x minus 1 is the inside, right? So remember, derivative of cosine is negative sine. Then you have to plug in the inside function, so that's why you have negative sine of x minus 1. But then times derivative of the inside. But what's the derivative of the inside function? What's the derivative of x minus 1? That's just 1. So we just leave it as negative sine of x minus 1. You okay with this? All right, good. Let's see. Let's put the second one. What is it? Okay, so as f of x equals x squared times square root of 1 minus x squared. Okay, so I saw several of you were trying to do chain rule right away. Remember, you have to look at this function. The first thing that's happening here is that you're multiplying 2 functions. This is a product of 2 functions, right? So to find this derivative, you need to use product rule, okay? Now, as you do the product rule, at some point you will need to figure out the derivative of this radical. There, you will need to use quotient chain rule because this little radical here is a composition of 2 functions. Yes, but that comes later. What dominates here right now is the product rule, so we're going to do that. Okay, so f prime, product rule. Derivative of the first is 2x times the second function plus first function times derivative of the second function. Now, just to make things a little bit organized, let's just leave it in symbols. And now in the next step, I'm going to go ahead and compute the derivative. Okay? So this is what we obtain when we use product rule. Now, of course, we're not done because we still need to figure out what is this. Now, here in this part, that's when chain rule takes place. Do you understand this? Questions about this line? Okay, so now I'm going to find this derivative, and in there we're going to use the little chain rule. So let's focus on this one now. Do you see the composition that's happening there? What's the outside function? Square root of x. And what's the inside function?
1 minus x squared.
1 minus x squared. Okay. So, just going to keep writing this. Okay. So now, inside the parentheses, let's put the derivative. So what derivative of this is derivative of the outside. What's the derivative of square root of x?
1 over 2 square root.
1 over 2 square root. But then we have to plug in the inside, right? And times derivative of the inside. What's the derivative of the inside?
2x.
Negative 2x. Do you understand? Okay, and now we just need to clean this up. So let's see. So I have a negative there, so it will be a minus. Notice that these 2 cancel with these 2 over here. So x squared times x. So I'm going to have an x cubed. And this quantity. So this is what we get so far. And you may want to stop there, but I'm going to go ahead and combine. And this way, you know, we practice a little bit. And that's nice because it's going to get rid of the radical on top. So here I'm going to multiply top and bottom by the square root, so I have the same denominator. Okay? But when I multiply top and bottom by the square root, I get 2x times 1 minus x squared. Now combining this, I'm going to strip with the parentheses. So we have 2x minus 2x cubed, then minus x cubed. And now we can combine nicely, so we get 2x minus 3x cubed. And for example, if I had asked you now find the points at which we have horizontal tangent lines and so on, which means you have to solve for the zero of this function, now it will be a pretty easy thing to do because you set the top equal to 0, and then you can see what the solutions are, right? You can factor this, factor out an x, and then you find your zeros. Okay?
If we left it like the first answer, is that okay? Like,
It is okay if the question is about derivative.
okay.
But next chapter, I'm going to ask you questions about the derivative, and so you have to be able to simplify and get here because we do stop with this. For example, if here I ask you, when is this greater than 0? When is the derivative greater than 0? This is harder to analyze from this point of view. You have to be able to do this because once you have this, then it's pretty easy to do it in this particular case. Okay? All right. So, but yeah, if you stop at this point, then that's good. That's okay. If the question is just find derivative, that's fine. If I said find derivative and simplify as much as possible, you know, that's a different story. Questions? Okay, good. So that was number 2. Again, if you have questions, ask. All right. So that was number 3. Okay, so 3x minus 1 over x squared plus 3, all of this squared. Okay, so remember, before we needed to use product rule first. And then it turned out that in a little step, we had to use chain rule. Now here, what takes precedence or what has priority? So we see a fraction, so you should probably imagine quotient rule at some point. But what do you think we should do, quotient rule or chain rule first? Chain rule, because what we have here really is a composition. X squared with this function. Do you see that? So chain rule needs to be used. In fact, here we can just do it quickly by using the general power rule. Okay? So let's do that. So y prime is bring the 2 down, keep the function. Subtract 1, so just do the 1, then times, again, I'm going to use the symbols just to organize the word. The derivative of the inside. Do you understand this? So that was in a power rule. Now, of course, we have to finish. So we need to compute this derivative, and whatever we do, the result has to be multiplied by this. So now, to find this derivative, what rule do we use? Quotient rule. Let's do it. So that's 2 times this. Times, now I'm going to use quotient rule. So quotient rule, derivative of the top,
3x.
3 is 3 times the bottom
X squared plus 3.
minus the top
3x minus
times derivative of the bottom. What is it?
2x.
2x divided by the bottom square. Do you understand this? Okay. Now just simplify. Again, here it's not acceptable to leave it like this. Okay? Don't leave it. I mean, you do this. If you get this, then I'll give you half the points because you technically took the derivative. But then you have to clean this up. Okay? So you have to simplify. Now it's algebra. The calculus is done. There is no. Now it's just algebra what we're about to do. Okay. So let me just multiply the top and combine like terms. See what we get. So this is 3x squared plus 9, and then minus 6x squared plus 2x. Okay, so I'm gonna go ahead and multiply. So we get 2 times 3x minus 1, and then 3x squared minus 6x squared, that's a negative 3x squared plus 2x plus 9 over x squared plus 3 cubed. And then just wondering, let's see, the number flow is negative 27 and the sum is negative 2, or the sum is positive 2. 27 is only 9 and 3, there's nothing more there, and there's no way you can get to 2 with 9 and 3. So you cannot factor this nicely at least, okay? Because maybe you go factor and then simplify something, but that's not going to happen, so we leave it like that, okay? If you don't like that negative 3, for example, I don't like that negative 3, I prefer to factor it out the negative and write it like this. But if you stop at the previous step, that's fine, okay? All right, questions? Once again, this is now, if I ask you when is this equal to 0, then that's something that you can also do very nicely because you set the top equal to 0. This is, here you get 1 over 3, and this one you square the formula. Okay? So you can find those points. That's how it is. If I ask you when is this greater than 0, you need to find zeros at the top and zeros at the bottom. The bottom is always positive, doesn't have zeros, so you don't care about that. It's just zeros at the top. You know how to find them and then put them in a line and do your interval test stuff. We will talk about that again next chapter when that type of questions arise. Okay? The point I'm trying to make here is that you have to be able to clean up and simplify. Otherwise, you're going to be stuck in the next chapter. Okay? All right. Questions? Are you okay? Okay. So 4. Okay, so 1 plus sine cube of x to the 5, all of that. Okay, so when you look at this, what's the first thing that comes to your mind?
General rule.
The chain rule or general power rule, right? Because we see something to the 12th power. Does everybody agree with this? So the first step here is to find that, to use the general power rule. So y prime is 12 times this stuff to the 11, right? But then remember, times derivative of this, right? Which is the thing that's being raised to the 12th power. So times derivative of 1 plus sine cube of x to the 5. That's the first step. You okay with this? Now, of course, we have to focus on this derivative. Now, to find this derivative, what do we do? Well, this is a sum. The derivative of a sum is the sum of the derivative. This one is easy, that's 0. How about this one? What do we need to do to find this derivative? Chain rule, because we have several compositions taking place here, right? How many functions do we have here?
3.
3 functions. Does everybody see them? x cubed is 1, sine, and then x to the 5. Okay, so let's do it. Okay, so I guess I'm gonna write here an extra step. So when we take derivative, we get 0. So that 0 we can just ignore it, and then we get times the derivative of. If you want, let me just 0 plus derivative of this. Okay. Now I'm gonna do this the long way, and then I'm gonna show you the type of shortcut that I like to use when I have a bunch of compositions. Okay. Otherwise, a problem could take you an entire page when you can really do it in one line. Okay, but you need to understand to be able to do it in one line what's happening. So let me first show you the long way, which just means that we're gonna be doing, chain rule anytime that the need arises. For example, here we can kind of circumvent that a little bit because it's true there are two compositions here, but the first one we can think of it as another general power rule because we have sine cube. You see that? So I'm gonna use power rule here, general power rule. So we get 12 times this. We just keep on writing this. Now here, I'm going to use the general power rule. So that's 3 sine square of x to the 5. Yes? And times derivative of the inside. What's the inside here? Sine x to the 5. Good. So times the derivative of sine of x to the 5. Do you understand this step? So again, I'm just taking this derivative now. So I use general power rule. Bring the 3 down, subtract 1. That's what this gives you. And then times the derivative of the inside, which is sine of x to the 5. Yes? Now, let's do this. What do we do here? The regular chain rule, right? What's the outside function? What's the inside function? Okay, so let's do it. So let's see, the 3 and the 12, that makes it 36. And you have sine square of x to the 5. Now times, now let's use chain rule. So derivative of the outside, what is it? Cosine. Plug in the inside function. Times derivative of the inside. What's the inside? 5x to the 4. So this, give me this. Do you understand this? And now we just clean everything together. So put everything together. So let's see, 36 times 5, that's 30, 15, so that's 180. So 180, I'm gonna put the x to the 4 here in the front. Then the 1 plus sine cube of x to the 5 to the 11. Then times sine square of x to the 5 times cosine of x to the 5. And that would be the final answer. Okay. Questions? So what I'm trying to tell you is, even though you may need to write a little bit more, organize yourself. Don't try to go ahead and write all the derivatives at once and have a bunch of stuff together because then you're gonna confuse. You can make mistakes. Just write one step at a time. I did my general power rule, then times this derivative. I'm done with that. Now I know that I need to focus on that derivative and then times this stuff, of course. Okay? Then the next step. Okay, that's a sum. It's 0 plus this derivative. Okay, write it. Now focus on this derivative. Keep on doing that. Okay? Use the notation that you have at your disposal so that you can organize your ideas. Otherwise, you can get lost pretty quickly. When the function is too big, then there are too many things going on, and then it's really easy to lose track of what's going on. Questions? Do you understand what's written on the board? Okay. All right. So the next one. So what was number 5? 5 was, okay, so this one now would be easier to deal with. Let's see, who can tell me what's the answer for this one? What's y prime? Negative sign
3x squared
of 3x squared
times 6x.
times 6x. Very good. Does everybody understand this? Outside function is the cosine, inside function 3x squared. The derivative of the outside is negative sign, plug in the inside function, times the derivative of the inside. Okay. All right, so questions? And number 6. That was square root sine. So here you can either use, here we can use the chain rule because we remember the square root of x. But if you don't remember it, my advice is write this as sine of x to the 1/2 and then use general power rule. Okay? However you want. Anyways, here we identify this composition, so we can go right away. So derivative of the outside,
1 over 2 square root.
1 over 2 square root, so but we have to plug in, so 1 over 2 square root sine times derivative of the inside, cosine. So we get cosine over 2 times square root sine. Okay, good. That was number 7. Sine cube of 4x. Okay. So here, this one I'm gonna do it the long way. Well, I already did the long way in the previous one. I mean, this is basically the same as what we did for this one. Right? The sine cube of x to the 5. Here we have sine cube of 4x. Basically, the same idea. So let me show you the shortcut. Okay. So in other words, you know, the long way is, okay, just use chain rule multiple times, like the general power rule, which is just chain rule first time, and then you recognize that there is another decomposition and use chain rule again. Instead of doing that, we could do this in one shot. And let's practice this as follows. So first of all, you need to be able to establish the entire composition. So what's the outermost function? X cubed, then sine, then 4x. So you understand that you have to use several chain rules, okay? So here is what you do. So you're gonna take the following steps. So you take the derivative of this guy and then plug in everything that is after that in the original line, okay? So the derivative is 3x squared. So y prime is gonna be equal to 3. Now, of course, you have to plug in everything that is after that. So that means collapse all of this together, you get sine of 4x. You understand what I'm saying? Just put one function inside the other one from right to left. And then here's what you're gonna do. So we were here, right? Then move your pointer, those of you that like programming, move it to the next time and repeat. Every time that you go over an arrow, you're gonna write times in here. Okay? So we started here, took the derivative, plug in everything, move over, that's the times, and now repeat the process. Do exactly the same thing. So now we're looking at the sign. For x, move over, put the times, and repeat. Derivative for x, that's 4, and then that's it. There's nothing else to plug in, so you hit the end, and you're done. Okay, so this way, even if you have 20 functions composed one inside each other, in one line you're gonna write down the derivative. Okay, now of course then you have to simplify and so on, but at least you don't have to worry about doing chain rule multiple times. We're doing it, but in this process we're doing it all at once. So we get 12 sine squared of 4x times cosine. Did you understand this? Yes? Okay, let's do the next one that has a bunch of functions inside the other one, and then let's use this procedure. Because here it will be very long to do it one step at a time with the chain rule. Okay? So for stuff like this, what I just told you is beneficial. So tangent cube or sine of the square root of 2x plus 1. So tangent cube of sine of the square root of 2x plus 1. Okay. Does everybody recognizes that there are several compositions taking place here? Okay, so tell me the functions. Remember, always from the outermost all the way down to the innermost. X cubed, tangent, sine,
Square root
and square root,
2x
and 2x plus 1. Yes? And now, since you know that we're going to need it, let's go ahead and let's write down the derivative of everybody. Okay? Below. So derivative of x cubed,
3x squared.
derivative of tangent, secant square, derivative of sine, derivative of square root, and derivative of 2x, 2. Okay, so now let's begin the process. So we are standing here at the beginning, okay? So we want to do y prime. So we take derivative, we have it right there, so that's 3x squared, but then what do we need to do? Plug in everything else. So what's everything else? What's everything else? So start putting everything inside each other, right to left. So these two guys, they collapse into square root of 2x plus 1. Then sine of square root of 2x plus 1, then tangent of square of sine square root of 2x plus 1. You understand what I'm saying? Just start putting function into this one, into this one, into this one. Okay? So you're collapsing everything back. So that would be tangent of sine of square root of 2x plus 1. Okay? So I need another parenthesis. Okay. Then, so we're done. We did that. We took the derivative, collapse everybody and plug it in, then move. And every time that you move, you put a times and repeat. So a secant square, so a secant square of, collapse everything after that. And move, put a times, repeat. Derivative of sine is cosine, collapse everything after that. The times, repeat, collapse, move, the times, repeat. And you're done because you reached the end. Okay? So like I said, in one line you can write down the answer. Okay? Even if you have a bunch of functions. And it's a systematic process, it's a procedure, it's always the same thing. The alternative is, okay, then you have to use one chain rule. So one chain rule, then another one, and another one. 4 chain rules you have to use. So it's up to you how you want to do it. Then just make sure that you can, write these things. So we get here 3 times tangent. So it's tangent square, then times secant square of sine square root of 2x plus 1 times cosine of the square root of 2x plus 1 all over square root of 2x plus 1. That's the derivative. Okay. Questions? Are you okay with this? All right. So this is a good point to stop. So we are done with chain rule. Now the next topic that we're going to discuss that I will talk about on Friday is going to be implicit differentiation. Do you know what is an implicit function? Yeah, I talked about the topic, but I didn't. So when you define a function, there are 2 ways to define a function. You can define a function explicitly, and you can define a function implicitly. explicit definition means I give you the formula. Like if I tell you y equals, let's say, let me do something simple, 1 over x. I'm explicitly telling you what y equals to. Okay? This is called explicit. Now, I could implicitly also give you the same information. Instead, implicitly, I can tell you the following. X times y equals 1. I can give you an equation. The way that x and y are related are like this. Of course, here this is very straightforward. You see that these two things are equivalent because it's easy to solve for y. But for example, what if I tell you this? X squared plus y squared equals 9. Okay? Now, if I wanted to give you this explicitly, you try to solve for y, you run into an issue because you're going to have, 9 minus x squared, square root, but then you have to put plus or minus. So there are really two equations. There are really two explicit formulas inside this equation. But this is one curve. What is this? That's a circle. Already straight instead of the origin. It's not a function, but still something that we're interested in. Imagine that I give you a point here, and then I want to know the equation of this tangent line. Okay? So we would like to be able to, we know here y can be regarded as a function of x. Give me an x, you get an equation, you're going to get an output. In fact, we get two outputs. Okay? So y can be regarded as a function of x, but then of course I have to say what do you want, the upper or the lower half of the circle. So there are two potential functions here. The positive square root and then the negative square root. Which the positive one is the top part of the circle, the negative one is the bottom part of the circle. So the question that we're going to deal on Friday is how do we find dy dx in functions that are defined like this. So for circles, ellipses, and all of that business. Okay? And here you could solve for y. What if I give you something like this? X cubed plus 2x plus y to the fifth equals 7. Let me make it more complicated. Throw in an xy in there. Forget about solving for y. Here you cannot even do what we did down here with the circle. But still, for each x, you get a degree 5 polynomial, there will be at least one real solution. So then you can think of y as a function of x with some restrictions. I want to know what's dy dx. Okay? So this is what we're going to discuss in the next topic. And the idea is that to some extent, here we're just going to be using chain rule. If you can think of y as a function of x, so every time that you take derivative of y to the 5, what would be the derivative with respect of x of y to the 5? You think of y as a function of x, 5y to the 4 times y prime, general power rule. Because there is a composition right here. Y is like your u of x, okay? So y is a function of x, just that we don't know what it is, because we have an implicit relation. We don't have explicitly a formula. But we can still do it this way, okay? So anyways, I'll be talking about this on Friday, but if you don't remember this from college algebra, or if you didn't see this in college algebra, it would be nice if you read about implicit versus explicit functions so you can understand better what I'm going to say on Friday, okay? So make sure that you review those ideas.